Okay, I hope you have already seen my video on the concepts on what is meant by HR diagram. Now let us actually look at the problems. Okay, so if you have not seen this, just go back and see the first video on this. This is extremely important for you to solve the problems using this. Okay, I just crunched it. I have given a small overview of what is HR diagram, what kind of information that you can derive from the HR diagram. Okay, so this question has been taken from May 2002 paper because there are lots of problems present during those times. Okay, on HR diagrams and everything. The new syllabus has this one here. So the diagram below shows a plot of luminosity versus temperature for a number of stars. Okay, so this is luminosity along the y-axis, temperature along the x-axis. So these are the dots represent the number of stars over here. Indicate on the diagram the main sequence stars and the regions that contain the white dwarf and red giants. Now, if you remember this, what you can do is you can draw that the main sequence stars will always represent something like an S like here. From the top one to bottom, it looks like an S over here. So this will be my main sequence star. Just right here, this will be my main sequence star. So all the stars which are lying on this will represent the main sequence star. So all this will represent the main sequence star. Might be I will reduce this a little bit so it becomes more clear within the field of view. Okay, then what is he asking here? So we have represented main sequence stars. Let me write it down here. This is your main sequence star. Main sequence star. Main sequence star. Then the next is on the regions that contain white dwarf and red giants. Red giants, the topmost here, these are known as red giants. Maybe you can include this also. Include this also. Okay, let me just write out a new one. I will take a different color pen to introduce or let you know what is red giant. So this cluster of stars are called as red giants. These are the red giants. Then what is the next thing is asking here? Is asking you to find out where are the white dwarfs. White dwarfs are those which have a very high temperature but they are very small. Okay, so therefore let me put something else. Let me take this one here. This is your white dwarf. This is your white dwarf. This is your white dwarf. Okay. Next. The arrows on the diagram represents a change in the state of a star. How does the temperature, luminosity, and size of the star change in this process? That is being asked. Okay. Now towards it, so what we will do is we will look at where is the arrow here. Arrow is this one. So towards it, this arrow here. This is the arrow. This is the arrow here. Okay. So now, which star he is referring to a star over here. So what is so special about it? With respect to temperature, luminosity, and size of star, change this process. So now what can we say? Now let us look at this here. See, this particular star, okay, is becoming like this. Now what's happening to temperature here? See, temperature here was this one. Now the new temperature for either you take this anything you take over here, new temperature is this one over here. So what's happening? Temperature is reducing. Okay, the temperature. See, because you see here this could be like something like 5,000, and here it is 4,000. You can now say, take up my pen. Temperature reduces. Then what happens to luminosity? Now, which stars I am referring to? Let me refer to this star and this star. Okay, so these extremes. Now this star, luminosity. What happens to luminosity? Luminosity here. This is your luminosity for this star, and for this one, luminosity is here. So which means luminosity is increasing. Luminosity is increasing. And then what is the size of the star? Size of the star. What happens? Now you see the radius. As I told you, there is no radius being shown over here. Definitely, red giants are larger in size. I told you, okay, red giants are larger in size. So therefore, this has a larger size as compared to the main sequence stars. So as a result of this, you can say size also increases. Okay. So these are the three parameters that change when there is a transition from main sequence stars to red giants. Okay. Then next is describe briefly the physical process that leads to changes in temperatures, luminosity, and size. That means he is asking you why does these three things change? Okay, why do these things change over here? Now, first thing is that Okay, now here, when it is star is a main sequence star, the mass of the stars, what happens in a main sequence star? A main sequence star is a stable star, which means what? You have a star. In the star, there is a lot of mass over here, and at the core, you have hydrogen, which is fusion. Hydrogen fusion is taking place over here. That means hydrogen is burning over here, it is giving out some energy. Now, when the fuel here is completely getting depleted off, which means what? There is no more hydrogen left to fuse. What will happen? The hydrogen fusion will ultimately lead to helium. When there are a lot of helium over here and less number of hydrogen over here, then what happens? The core here becomes more massive. Okay. Initially, when you had hydrogen fusion over here, there's an energy which is present in the star. This energy is now being given outward like this. Given outward like this, which means it creates a sort of pressure which you call as radiation pressure. Okay, which means the star, the matter present in the star should not stay there itself. It should be exploded. But unfortunately, nothing like that happens. Okay, now why doesn't it happen? The reason is because there's a mass of these hydrogen nuclei which is present over here, which is trying to pull it. So there is a gravitational force dragging inside, and there is a radiation pressure which is acting outwards. These two balance each other. So as a result of it, the star is seen to be stable over here. Okay, so similar to that of an object kept on a table, you see there are two forces. What are the forces? One is a mg force which is acting here, but the table says, okay, I'm not going to let you come down, I'm going to put a normal force outward over there. The n and the mg balance over here, and it's standing there. It's stable. Of course, it's just an analogy, not exact thing over here. Okay, now this is what is happening over here. Now, when hydrogen fusion leads to helium, that means all the hydrogen are getting converted into helium. That means this is becoming more massive. This is becoming more massive, and the energies are all being thrown out over here. When this becomes more massive, what happens? There's a pull which is being seen over here. Okay. So, in other words, hydrogen fusion reduces. When hydrogen fusion reduces, what happens to temperature? Temperature also reduces. Temperature reduces. Okay, and when the temperature reduces, then what happens? So helium is being produced. Helium is being produced. When this star's gases, okay, or whatever has been getting burnt over here, it goes outward over here. Then what happens? Size increase. Size increases, right? It goes outwards and it increases the size. Okay, and then what else can happen? The mass of the star can increase. Because it's increasing. So as a result of it, when this goes outwards, luminosity also increases. Thus we have seen temperature reduces, mass of the star increases, size increases, luminosity increases. Let us look, have we mentioned all this? See, we have seen 1, 2, and 3. All this we have been mentioned. Okay. So with this we come to an end to this problem. We will see the next problem in the next video. Thank you.